All right, so the key idea that we're going to be using in all of these relates back to when we were talking about lines. So if we have a line that goes up as we move from left to right, we would say that it has positive slope. And we're going to refer to this as something is increasing when it has positive slope. And if a graph goes down as we move from left to right, we're going to say it has negative slope. And we're going to call this decreasing. And then the final option that is possible is when we have a horizontal line, we're going to refer to it as constant. And then this has slope 0. So these are the three possibilities for a graph. It can either be increasing, which means it has positive slope. It can be decreasing, which means it has negative slope. Or it can be constant, which means it has 0 slope. All right, so let's go ahead and take a look at our first example. So from the graph of the function, state the intervals on which the function is increasing, decreasing, or constant. So when we're doing problems like this, the first thing we want to do is identify where it's doing each of these things. So let's start with increasing. So from our picture above, increasing means it has positive slope, or that it's going up as we move from left to right. So this graph is increasing in two different places. When we're talking about increasing, decreasing, or constant, we're talking about these intervals right here. So we report only x values, because we're really talking about the domain. So when we want to talk about increasing, we're going to have our graph is increasing from here to here and here to here. We only want to talk about the x values. So our coordinate there would be -7, -3. And up here, our coordinate would be -1 and +6. And similarly, right here, we would have our ordered pair 4 and 1. And here we would have our ordered pair 6 and 5. But when we are reporting our places where it is increasing, we're going to take only our x values. So it's increasing from -7 to -1, and then or it is also increasing here from 4 to 6. So when we're writing our solutions, we're only taking the x values when we're talking about increasing, decreasing, and constant. Nowhere in there do we actually reference the y values. So it was increasing on this part where it's red, but it's increasing from x equals -7 to -1, and from x from 4 to 6, which is the two things we're going to write for our solution. Similarly, when we want to talk about decreasing now, our graph is going down as we go from left to right, from here to here, and here to here. So when we do decreasing, once again, we are only going to be talking about our x values. So on this first part where it's decreasing, we have -1, and it decreases until x is 4. And then, or our graph decreases again from 6 to, and then we have our ordered pair out here at 8, and it went all the way down to -5, which we don't care about, and it decreases from 6 to 8. All right. So, the last thing we need to do is figure out where this thing is constant. And that's this last little bit over here. So we have our constant, and we have our arrow pointing to the left, so it's going to be from -infinity up to our value here, which would be -7. So the place where people get caught up the most on these problems is we want to include y values. So when we're talking about increasing, decreasing, and constant, we report only x values, or our domain values. The y values are only there to help us see when the graph is going up or coming down. All right, so for example 2, we want to use from the graph of the function, we want to determine the domain and the range. So when we look at this same thing, domain and range, we may want to remember we had the following. For continuous functions, the domain it's going to be smallest x to largest x. And the range is going to be smallest y to largest y. Perfect. So when we look at our picture now, we want to find our domain. So our domain is going to be the smallest x to the largest x. So our graph's got the arrow that it goes on forever and ever in this direction, right? So that would make our smallest x is going to be -infinity. And then our largest x, we get to right here. And as we noted before, the ordered pair is 8, -5. But it also has the open circle. So that means it is not included. So then our largest x would be the value of 8, but not included, right? So it gets a rounded parenthesis. And now we want to talk about our range. And our range is going to be the smallest y to our largest y. So once again, we look at our graph, and what's our smallest y value going to be? Well, our smallest y value is going to be coming from this point, so we look at our y, and our smallest y value is going to be -5. But once again, it is not included, so it gets a rounded parenthesis. Now we look at our graph, our largest y is going to be up here. And the ordered pair of that point is going to be -1 and 6. So our largest y value is going to be 6, but our graph actually makes it to that y value of 6. So we're going to put it in a square bracket because it's included. So then our range would be from -5 all the way up to +6. All right, so for try number 1, we want to determine when it's increasing, decreasing, or constant. So let's go ahead and take a look at increasing. So we're going to be increasing here and here. So for our increasing, we're going to increase from -6 to -5, unioned with -1 to +3. And then our graph is going to be decreasing from here to here. And so it's going to be from -8 to -6, unioned with (3 to 7). And then lastly, we have our constant bit, which is right here. And we're going to be constant from -5 until we get to -1. So that gives us our increasing, our decreasing, and our constant. And now we want to determine the domain and range for our graph. So our domain is going to be our smallest x to our largest x. So our smallest x value occurs right here and is going to be from -8, and we have a filled in dot, so it's included, to our largest x, which is up here, which is going to be 7, but it's a hollow dot, so it's not included, so it gets a rounded parenthesis. And then we have our range. We need our smallest y, which is going to be here. So it's going to be 2 to our largest y, which is going to be up here at 7. So our range is from 2 to 7, and our domain is going to go from -8 to +7. Okay, so hopefully we're feeling okay with those for a second. So now let's take a look at our next one. So our same graphs are coming back again, but before we talk about those graphs, we do need to write down a couple of things. And we have the following. If f of x is a continuous function, the graph will always change from increasing to decreasing at a local maximum and from decreasing to increasing at a local minimum. So the next thing we want to note is that if we see the word local or we see the word relative, they mean the same thing. So what I mean by that is if we have a local max is the same as a relative max. And the same thing holds for mins. So basically, local and relative are synonyms, is what I'm really trying to say. Sometimes you will hear them referred to as local. Sometimes you will hear them referred to as relative. Either one means exactly the same thing. So when you hear local or relative, we're talking about the same idea. So this next part should be a little bit intuitive. So imagine if you throw a ball up into the air, what happens? It goes up, it goes up, it goes up. Eventually the ball stops going up, so instantaneously the ball is going to stop, and then what happens? It starts falling back towards the earth. Well, at that point where it stops going up, it stops instantaneously and then turns around and comes back down, it's going to have a local maximum. Well, that means it changed from increasing to decreasing. Similarly, if something is going down, it stops and turns around and goes back up, it's going to have a local minimum. So that's really all that this is saying, is that we're going to have local maxes and local mins where it changes from increasing to decreasing and decreasing to increasing. So if we take a look at example 3, which is the same picture that we've been working with in the other ones, we can use our previous work or just look at our graph to help us see what is happening. So we want to identify our local max and our local min. So we have our graph changes from here, it changes from increasing to decreasing, which would make this a maximum. And then here, our graph changes from decreasing to increasing, so that would be a min. And then it changes once again from increasing to decreasing, which would make this a max. So our graph has a local or a relative max at the points. So our first ordered pair is -1 and 6. And our second one is at 6 and 5. We have our min is located at the point 4 and 1. So our local maxes and mins, or our relative maxes and mins, occur only when the graph changes from increasing to decreasing and from decreasing to increasing. So let's keep that in mind as we look at our next you try. All right. So for this, we want to identify our relative max and our relative min. So remember, the key to this is that a relative max, it has to change from increasing to decreasing and from decreasing to increasing at a local min. So our graph, here it's going down and then starts going back up. So that's going to be our min. And over here, our graph is going up and then starts going back down, and it's going to be a max. So one place we have to be careful with is right here. This is neither, because our graph goes from constant to increasing. So since it wasn't decreasing to increasing, it's not going to be one. And this one is also not a max or a min, because it doesn't change from increasing to decreasing or from decreasing to increasing. So not max or min. So really, what we have to be on, what we're observing for is changing from decreasing to increasing or changing from increasing to decreasing. And those will be exactly the points where that happens. So our min is located at the ordered pair, -6 and 2, and our max is located at the point 3 and 7. All right. So our next example wants us to graph the function and then estimate the intervals where the function is increasing or decreasing, and then find our local maxes and our local mins. So this one is graphing calculator food. So let's grab our graphing device and draw ourselves a picture. So we wish to graph our function. So we go to our y equals menu, and if we have anything in here, make sure we clear it out. And we want to graph 5 minus the absolute value of x minus 2. So we go 5 minus, and remember, to get our absolute value, there are 2 ways we can do it. The fast way is we press alpha and window, and we choose choice number 1 for ABS. We can also find it by going into our math menu as well. And then we type in x minus 2. So our expression, our function looks exactly like our function here. And we go ahead and we press graph. And I've got mine all messed up, so I'm going to turn my plots off. So second y equals, turn my plots off. And then I want my standard window, so I'm going to hit my zoom key and choose choice number 6. And that gets us back to our regular old graph. So now we've got our graph, and we're going to be using our eyeball metric to determine what our solutions are. So it says estimate, so that's how we know we're using our eyeballs to guess, is we're estimating. So this point looks like a local max right here. And it is located using the eyeball metric, 1, 2, 3, 4, 5 right here. So it appears to be at the point 2, 5. So then that would be our local max. And now we want to know where it's increasing and where it's decreasing. So it looks like it's increasing from here to here. So it increases to our local max, so that's from -infinity to 2, and then after our local max, it's going to decrease. So we are going to decrease from 2 to positive infinity. And just as a bonus question, we weren't asked this, but what would its range be? Well, smallest y to the largest y. Well, what's our largest y value going to be? 5. So then we're going to get that our range goes from -infinity to 5. So example number 5 is an example of what's called an optimization problem. So when we break these down, we're going to break them down into 2 different parts. So we're going to have what's called our objective function, and we're going to have what's called a constraint equation. So whenever we have an optimization problem, we're going to need to identify these 2 parts. So a farmer is building 2 pens of the same size next to a barn. If she has 300 meters of fence, what is the maximum area of each pen? So I've included a diagram of what we have here. So our objective function is really going to be, well, what's our goal? Not in orange. So our goal in this case is what is the maximum area of each pen? So we need to label this, and we look at our pens, and our pens are rectangles. So, and we want to talk about an area. So the area formula for a rectangle, which will be our objective function, is length times width. So I'm going to label my lengths and my widths. So I made the L's perpendicular to the barn and the widths parallel to the barn. If you would have done them in the other order, you're going to get the same answer in the end. It doesn't matter. It's just dealer's choice. That's how I picked to label my diagram. If you use something else, that's fine too. So our objective function is what we are trying to do. Well, we could make those pens as big as we wanted if we have an infinite amount of fence, which we don't. In real life, we're always going to be constrained. You never have an infinite amount of money, an infinite amount of fence, or an infinite amount of resources. Everything is going to be finite. So what is our constraint in this case? Well, our constraint is the fact that she has 300 meters of fence. Well, that's going to be a perimeter. So we look at our pens, and our perimeter is going to be, we have 3 L's, so 3L, plus we have 2 W's. 2W has to equal the amount of fence that we have available to use. So we have our objective function and we have our constraint function. So now that we have these two things, the way this is going to go down is we will solve the constraint equation for a variable and substitute it into the objective function. So in the constraint equation, we have two different variables. We have L and W, and it says just solve it for a variable. There is no wrong choice. So if you solve it for L, you're going to end up in the end with the same answer as if you solve it for W. So I am going to solve my constraint equation for L just because I'm picking L. If you pick W, you'll get the same answer in the end. So to solve for L, I minus 2W, and I minus 2W, and that gives me 3L is equal to 300 minus 2W. And then I divide by 3, divide by 3, and divide by 3, and that gives me that L is equal to 100 minus 2/3 W. So our goal then is, now we've solved the constraint equation for a variable, now we're going to substitute this back into the objective function. So we substitute it back into our objective function, and I highlight the wrong one. Thank goodness I'm a cheater, and I can just erase. Back in for L. There we go. So we're going to substitute what L is back into our original objective function. So we get A is equal to, we replace the L with 100 minus 2 over 3W times the W. So this is us substituting it in. So now, instead of our objective function having 3 variables, it now only contains 2 variables. We can now graph this with our graphing device. So we're going to graph this with our TI calculator. And our calculator only knows x's and y's. So just to be explicit and to help me keep track of what everything is, A is going to be our y and W is going to be our x. So now I'm going to put those into my calculator. So I have y equals, clear out what I have in here, parenthesis 100 minus, and then the alpha y equals gets me my fraction, so 2 over 3 x, close our parentheses, times x. And now I'm going to go graph, and I'm like, drum roll please, and I get nothing. Well, why is it that I'm not seeing anything? Well, it's just like when we did our activity, it's because my window's not looking in the right place. So I need to change my window. So I'm going to go window, and if I go back to the diagram, it's going to give me some hints on what I want to change my window to. I know I only have 300 meters of fence, and I know W is playing the role of X. Well, I have 2 W's and 300 meters of fence, so the biggest W could be, well, 2 W's equals 300 would be W, the biggest value it could ever be is 150. So I'm going to have my X min as 0, and my X max as 150, and I'm going to change my Y scale to 10. And then Y is playing the role of area, and that one we're just going to have to guess. So area has to be positive, so I'll make Y min 0, and then I'm just going to guess something for Y max. And I'm going to say 1,000. And then I'm going to change my Y scale to 100. And I graph, and I'm like, okay, well, I can see something, but can I see the entire graph? And the answer is no. And that's because I made a bad guess for my Y value. My graph goes off the top. So I didn't pick a big enough Y, and it was just a guess, and that might happen. So you just press window again and make a bigger Y max. Well, 1,000 wasn't a big enough, so I'm going to make it 10,000, and then I'm going to change my Y scale to 1,000. And when I press graph this time, that was plenty big as a guess. So if at first you don't guess right, that's okay. Just go back into window and keep guessing until you get a window that shows you what you want. We're trying to find our local maximum. Well, the eyeball metric tells us, oh, well, it's right here on my calculator, but unfortunately I can't put right here into my labs or my right here onto an exam. So we see that our max is going to be somewhere about right here. So to find the local maximum on our calculator, we're going to go into our calculate menu. So we press second and trace on our calculator. And we've been in this menu before to find zeros and intersections. This time we'll notice choices 3 and 4 allow us to find minimums and maximums. So we're looking for a max. So we're going to select choice number 4 on our calculator. And then similar to the zeros, it's going to ask us 3 questions. We pick something on the left, we pick something on the right, and then we're going to guess. So remember, when it says left and right, it's talking about x values. So I moved my cursor to the left of my maximum, and I guess. Oops. And then move my cursor again to where I'm to the right of my maximum. Okay, it's starting to go down. I hit enter. And then it says guess. You just move back closer to the maximum and you press enter, and it's going to give us this as a value. So now our calculator has actually found our maximum, and it gives us our x and our y. And notice for our x, we have 74.99999. We should just round that to x is 75, and our y is 3750. So now we go back up here. x was our width, so that tells us that w, the width, is 75 meters, and that y was our area. Remember, that was A. So the area is going to be 3,750 square meters. Yeah, so let's recap how we would do that on the calculator again. So we're going to go into our calculate menu. So we go second and trace. And that gives us our calculate menu, and we're looking for the maximum. So we go down to choice number 4. And then we have to answer the 3 questions: left bound, right bound, and guess. So we move our cursor to the left of the maximum, press enter. We move our cursor to the right of the maximum, press enter. And then we move closer to the maximum, press enter. And once again, it'll think, and it gives us where the maximum value would be located. So notice we found the width and the area, but that doesn't completely answer the question. What else do we need? The length, right? Because we substituted the length out of the original problem up here in this step. So we can either use this formula to find the length. So the length is 100 minus 2/3 w. So the length is 100 minus 2/3 times w, which is 75. And we can type that into our calculator, or note 3 goes into 75 25 times. 2 times 25 is going to give us 50. So 100 take away 50 gives us 50 meters. So the width would be 75 meters and the length would be 50. We could use that formula, but we also know that area was equal to length times width. And we had the area was 3750, and L we didn't know, and the width was 75. And you'll notice if you divide both of those by 75, you will also get exactly the same thing we did as using the other formula. So 3750 divided by 75 also is equal to 50, right? Because there's multiple different ways that we can get oops, undo. All right, so let's go ahead and jump to our next example. So example 6 is going to have us do the same thing, but it's kind of got the problem broken down into a few different parts for us. So a triangle with a base of x and a height of y is inscribed in a semicircle with a radius 5 as shown below. We want to express the area of the triangle as a function of x. So we look at our triangle, we have our semicircle. So if we assume that this is 0, 0, the equation of a circle with center 0, 0 from chapter 1 was x squared plus y squared equals r squared, and our radius was 5, so 5 squared is 25. So then that would make this side x and make this side y on our triangle. So part A is really asking us to find the objective function. So the area formula for a triangle is 1/2 base times height, which is 1/2 x times y. But it wants us to express it as a function of x, which means we need to substitute out y. Well, what is it that is constraining this triangle? Well, it's the fact that this point is stuck on that semicircle. Well, the semicircle has the equation x squared plus y squared equals 25, This is going to be our constraint. So just like what we did in the previous problem, we have our objective function over here, and we have our constraint. So this one says specifically we want to have x's left, so we're going to solve this for y. So we minus x squared, we minus x squared, and we get y squared equals 25 minus x squared. We take our square root, so y is the square root of 25 minus x squared. And once again, we're going to substitute this into our objective function. So that gives us the answer to part A. So it's 1/2 x times the square root of 25 minus x squared. So then let's go ahead and use our graphing calculator to answer the next two parts. So we go to our y equals this time, and we're going to go 1/2 times x times the square root of 25 minus x squared. And we press graph, and of course we can't see anything because I have my window all messed up. So to get back to my regular window, I go zoom, and I choose choice number 6. We graph, and then to find it exactly, we're going to use the same thing we did before. We go second, trace, we choose maximum, we have left bound, and then I'm going to scroll over past the max. So I go over here. I went way farther than I needed to, and then I scroll back to the maximum, and I press enter, and my eyeball metric was reasonably close. We eyeballed it to be about 3, and it looks like the actual answer is 3.5 for our x, and the area would be 6.25 or 6.25. So that gives us our x. To find our corresponding y, we would plug that back in. And just as a reminder, remember our calculator saves the x value as long as we don't do any other computations. So to plug that back into our formula, we would just go the square root of 25 minus x and squared. We press enter, and that would give us the corresponding y value.
Sorry, Professor, just to answer those 3 questions after you hit the maximum, how far left do you go and how far right do you go in order to get the 3.53 that you got?
So we go back, and we can get our domain from our calculator. So from -5 to 5. So for B, we look our domain. At first glance, it looks like it's going to be from -5 to 5. So that's part B. We're going to come back to that in a second. Part C, we graphed it. Check, that's done. D, what dimensions maximize? And that's going to be these. So that's our x and our y. So D, this was C, and then our x is going to be about 3.54, and y is going to be the same thing, about 3.54-ish. All right, so we have to be a little bit careful because graphically when we look at B, the graph tells us that that's the domain. If you try to put that into MyLabs, it's going to tell you you're wrong. And we have to be a little bit careful because what's our constraint equation? It's an area formula, right? So what do our x and our y have to be? Can my height be -5 feet? No. No matter how much I want it to be, can I have a negative height? No, it's not possible. So in problems, application problems, where we're dealing with things like this, our domain is actually going to be from 0 to 5. So just be a little bit careful with this because distance can't be negative. So the math doesn't care, but you can't be negative 5 feet tall no matter how much you want to be. So distances always have to be non-negative, so that's going to start at 0. So the next thing we want to talk about are piecewise defined functions. So let's talk a little bit about their anatomy. So a piecewise defined function is going to be a function as we normally see it, but it's going to have multiple rules. So rule 1, and with each rule there's going to be an associated domain. And we have rule 2, domain 2, all the way down. We can have as many rules as we want, rule n and domain n. So the way this is going to work is it's going to be a lot like a regular function, but when we're given an input x, the first thing we have to do is decide which domain the x belongs to. And once we find the appropriate domain, we will then use the rule that is associated with that domain. And I know right now this isn't clear at all. The next example will help us see what I mean by that. So let's take a look at this. So we have our piecewise function here, f of x. And in our piecewise function, it has 3 parts. So we're going to have our rule 1 and domain 1. Here's rule 1 and domain 1. We're then going to have rule 2 and domain 2. And then lastly, we're going to have rule 3 and domain 3. So when we are asked to find f of negative 5, we have to decide, first thing, which of these 3 domains is negative 5 in. So is negative 5 in green, is negative 5 in red, or is negative 5 in blue? So when we look at negative 5, we have to ask ourselves the question, is negative 5 less than or equal to negative 2? And the answer to that question is yes. So negative 5 belongs in the green domain, which then means we are going to put negative 5 into the green rule. So 1/5 times negative 5 take away 2. And then we simplify. So 1/5 times negative 5 is negative 1 minus 2 gives us negative 3. So f of negative 5 would be negative 3. To find our next one, f of 0, we have to look at our input 0 and decide which domain it is. Well, is 0 less than or equal to negative 2? No. Is 0 in between negative 2 and positive 1? And the answer is yes. So 0 belongs in the red domain, which means then, instead of putting it into the green rule like we did for negative 5, 0 is going to go into the red rule. And our red rule is just equal to 1. Right? It's just a 1, there's no x's. So f of 0 is going to be 1. Lastly, we look at our last one, and we have f of 1, and we need to decide which domain it goes into. Well, is 1 less than or equal to negative 2? No. Is negative 1 bigger than negative 2 but less than or equal to positive 1? And the answer is yes. So that's also in the red domain. So we look at our red rule, and the red rule is just 1. So a couple of things we want to look at here. Each input, or each x, so like negative 5, 0, and positive 1, will belong in one or exactly one domain. So it can't go into more than one rule. So we're just looking for the rule it belongs to. And then we put that input into the corresponding rule. So just as a bonus for this one, if I said find f of 3, which colored domain would 3 belong to? Well, 3 is not less than negative 2. 3 is not bigger than negative 2 and less than or equal to 1. 3 is bigger than positive 1. So 3 would belong to the blue domain, which would mean it would go into the blue rule. So I would have negative x squared take away 1, where my x is 3. So then I would simplify that. So 3 squared is 9. So I would get negative 9 take away 1. That's going to give me negative 10. And that would be my corresponding output for f of 3. So for each of these, each input will belong to exactly one domain, and then we put that input into the corresponding rule. So it's like the functions that we've used before, but now each function is built out of other functions. And that's why we refer to this as a piecewise function. So now we need to graph this thing using our graphing calculator. So now let's all grab our graphing device and let's draw ourselves a nice picture. So we grab our graphing device and we want to go ahead and graph this. So I'm going to open my y equals. I'm going to clear out what I have here. So when I put this into my graphing calculator, I need to put each rule in parentheses. So my first rule is 1/5 x take away 2. So I'm going to go parenthesis, and then I type my 1/5 x, so alpha y equals gets me my fraction, 1 over 5, x, take away 2, close my parentheses, then I'm going to put my domain in. My domain also needs to go into parentheses. So I open my parentheses, and then I have x, and then to get my less than or equals to sign, I'm going to go into my test menu. So if you look at the secondary function on your math key, you'll see its second function says test. So you're going to hit second, and then math, and that opens up your test menu. And we need the less than or equal to. So I scroll all the way down to number 6 and press enter, and then I'm going to do -2. All right, we're not done with this yet. We're going to come back and add more, but just to show you what happens after you type this in, let's go ahead and press graph. So my calculator draws 1/5 x minus 2, and notice, where did my calculator stop drawing? What was the input where it stopped? -2. Because we're only using the green rule for x values that are less than or equal to -2. So this was the green rule, and it stops at -2. All right, let's finish graphing this thing. So we press our y equals, and it brings us back in. So we're going to scroll now all the way to the end of that rule to where we just did our domain. To put in the second part, we press our plus key. So we do plus, and then we're going to do the same thing. We put each rule in parentheses. So I go parenthesis 1, close my parenthesis, parenthesis, and now I need to put my rule in. So for this next part, we have to be careful. So before I start typing, to put this in our calculator, I have to break up the and into two parts. So it's -2 is less than x, and then I'm going to, so I have -2 is less than x, and then another parenthesis, x is less than or equal to 1. And this is what I'm going to need to type into my calculator. So we grab our calculator. I've got my rule, but I'm now going to put each of those domains in. So I go -2 is, and then second test, less than is choice number 5, x, and I close those parentheses, open another set, and I go x into my test menu again, is less than or equal to 1, and I'm going to close my parenthesis once again, and now I'm going to press graph. We're still not done. So there's my green rule, and then what does my red rule look like? Well, it was 1, and where is my values equal to 1? In between -2 all the way out to +1. So now we need to finish putting it in. We still haven't put in our blue rule, right? So we press our y equals again, and I'm going to scroll all the way to the end of this. So there's my next rule. So I do plus again, parenthesis, and my blue rule is -x squared, take away 1, close my parentheses, open my parentheses, and my domain is x, second math to get my test menu, x is greater than 1. And I close my parentheses. Finally, I've got my green, my red, and my blue. So I do graph. And we get something that looks like this. All right, so now I've got my graph here, and just to make it explicit, so this is my green part of the graph, this is my red part of the graph, and this is my blue part of the graph. So our calculator is good at drawing the parts, but it doesn't do the open and closed circles. So we'll notice on the green domain at -2, I have a less than or equal to. So that means on my graph, this would be a filled in circle, and on my graph, that would be an open circle. Then on my red graph, see, open not included, less than or equal is included, so that's going to be a filled in circle. And then on my blue graph, I have a greater than but not equal to, so then that means that one's going to be an open circle. So that would be what our graph would look like. And if we check our inputs, let's take a look. If I go to -5, 1, 2, 3, 4, 5, or -5, 2, 3, 4, -5, and then I go over here, well, what's the corresponding y value? Oh, -3. That's exactly what we got when we evaluated it manually. If I go to 0 and I go up to my y value, well, what's my red y value there? 1, as we expected. And if I go over to 3, 1, 2, 3, we see my graph does go all the way down to 10 right here. So we see that this graph does indeed represent that piecewise function. So we can graph it by putting all of these parts together.